Moon's origin, the cataclysmic collision that shaped our night sky. For millennia, the moon has captivated humanity. It's a celestial beacon, a source of myth, and a constant companion in our night sky. But have you ever wondered how this familiar orb came to be? The leading scientific explanation points to a dramatic event in Earth's distant past, the giant impact hypothesis. This theory proposes that our moon was born from a cataclysmic collision between the early Earth and a Mars-sized protoplanet named Theia. Prepare to journey back billions of years to witness this colossal cosmic crash. We'll explore the science behind the giant impact hypothesis and uncover the evidence that supports this incredible story of lunar formation. The early solar system was a chaotic arena. Protoplanets swirled and collided as gravity sculpted order from primordial dust and gas. It was in this tumultuous environment that the seeds of our moon were sown. Enter Theia, a protoplanet roughly the size of Mars. This celestial body was on a collision course with the young Earth, a planet still in its formative stages. Around 4.5 billion years ago, the inevitable happened. Theia and Earth met in a cosmic rendezvous of unimaginable force. This wasn't a head-on smash. Instead, Theia struck a glancing blow, a high-speed impact that forever altered the destiny of both planets. The energy released during this collision was immense. The impact vaporized vast amounts of rock and metal, creating a superheated cloud of debris. The force of the impact ejected molten rock and gas into orbit around the Earth. This material, a mixture of Earth's mantle and Theia's remains, became the building blocks of our moon. The composition of this debris was crucial. It consisted primarily of material from Earth's mantle and a significant portion of Theia's core. Under the relentless pull of gravity, this orbiting debris began to coalesce. Particles clumped together, gradually forming larger and larger bodies. The time frame for this lunar formation was surprisingly short. Some simulations suggest the moon could have formed in just months or years following the initial impact. Imagine a swirling ring of debris encircling the Earth. Over time, this ring coalesced, solidifying into the moon we see today. The giant impact hypothesis isn't just a theory. It's supported by a wealth of scientific evidence. One of the strongest pieces of evidence lies in the compositional similarity between the moon and Earth's mantle. Lunar rocks brought back by the Apollo missions share a striking resemblance to rocks found on Earth. This suggests a shared origin, with the moon formed from material originating from our planet. Isotopic ratios, the relative abundance of different isotopes of elements, provide further evidence of this shared origin. The moon's isotopic ratios closely match those of Earth, reinforcing the idea that the moon and Earth are related. The moon's relatively low density is another key piece of the puzzle. Compared to other rocky bodies in the solar system, the moon is surprisingly lightweight. This low density is explained by the moon's lack of a large iron core. Unlike Earth, which has a substantial iron core, the moon's core is relatively small. This lack of a large iron core is consistent with the giant impact hypothesis. Theia's core likely merged with Earth's core during the collision, leaving the moon depleted in iron. The giant impact hypothesis also explains the transfer of angular momentum to the Earth-Moon system. The impact imparted a significant amount of angular momentum, affecting the rotation of both Earth and the moon. This transfer of angular momentum explains Earth's rapid rotation early in its history. The impact sped up Earth's spin, resulting in shorter days. It also explains the moon's orbit around Earth. The moon's orbit is a direct consequence of the angular momentum imparted by the giant impact. Perhaps the most compelling evidence comes from computer simulations. Scientists have created sophisticated simulations of the giant impact, and these simulations successfully replicate the formation of a moon with the characteristics we observe today. Despite the overwhelming evidence supporting the giant impact hypothesis, some questions remain unanswered. scientists continue to investigate the precise details of this cataclysmic event. The exact nature and composition of Theia remain a mystery. Was it a differentiated body with a core, mantle, and crust, or was it a more homogeneous mixture of materials? The precise details of the impact event are also still under investigation. What was the angle of impact? What was the velocity of Theia? Ongoing analysis of lunar samples continues to provide new insights. Scientists are studying lunar rocks and soil to learn more about the moon's composition and origin. Continued development of sophisticated simulations is also crucial. These simulations allow scientists to test different scenarios and refine our understanding of the impact. Through ongoing research, scientists are constantly refining our understanding of the giant impact. Each new discovery brings us closer to unraveling the mysteries of the moon's origin. The giant impact hypothesis describes a pivotal event in Earth's history. It explains not only the origin of the moon, but also the evolution of our own planet. The moon's presence has profoundly influenced Earth's climate and tides. Its gravitational pull stabilizes Earth's axial tilt, preventing extreme climate variations. The tides, driven by the moon's gravity, have shaped coastlines and influenced marine ecosystems. The moon has played a crucial role in the evolution of life on Earth. From its formation in a cataclysmic collision to its enduring influence on our planet, the moon's story is one of cosmic drama and profound significance. It's a reminder that even the most familiar objects in our night sky have a history that is both awe-inspiring and deeply connected to our own.